All right, we are here still talking about beams. Today's topic is design of beams, although probably it's a little bit more better titled selection of beams from a standard set of beams. Although there are some design of beam elements that you can do where maybe the beam is very simple, like a rectangle, and you've got to figure out how thick to make the rectangle, something like that. We could imagine that being design of beams. But the topic that we're going to spend most time on is more selecting the correct beam from a set of beams that we have to choose from, the standard set. There was a question though about moments of inertia, because that's also related to beam, flexural stress in beams, and all of those sort of things. So let's look at that first, and then let's do design of beams. So let's see. Where do we need to go? Maybe find a beam here, or a cross section rather. Let's see. What do these look like? There's one we could do. Cantilever beam. That one's probably not useful enough. That one maybe. You know what? Let's probably just do that first one. Let's do that first one. All right, so this one, the point here is not that it's a complicated cross section. This is one shape. It's a half circle. The point for this one is that, well, it wants us to find some stress numbers, but it is asking for the maximum tension and the maximum compression flexural stress. But we can do some other stuff with this one too, just to show how some of this stuff works. So let's copy this problem. We'll solve this one, and then we'll do some stuff around this one. All right. So we are going to need our charts that show the moment of inertia for a half circle. So let's go find those. I would have those stored away over here, I guess. Let's see. Moments of inertia right here. And there's a half circle. Whoops. Oh, what is it doing? It's stuck on. There we go. All right. We can make that a little larger. There we go. All right. So the problem is actually telling us that we've got some beam this is the cross section of some beam. So normally you don't have beams that are half circles, but we do here. This particular one has a radius of r equals 1.7 inches, and then they've gone ahead and told us that they didn't give us the loading scenario at all. They just told us that the maximum bending moment is 21,800 inch-pounds about a horizontal axis. So the x-axis. So when they give us this maximum positive bending moment, that's, maybe they drew the shear and bending diagram or whatever. Somehow they found where this maximum bending moment is. It's probably useful to take a little bit of a second and describe two and a half scenarios where we can just know the location of the maximum bending moment. So one of those is a cantilever beam. So cantilever beam, I don't think we've done many cantilever beams, but there's your cantilever beam. And no matter what loads you put on this thing, however you put them, the location for the maximum bending moment is always going to be at the wall. So if you have one of these cantilever beams, then you don't have to go, if your point is to solve for maximum bending moment or maximum flexural stress where you need the maximum bending moment, then the point, you don't have to go and draw the shear and bending diagram or whatever. You can just know for cantilever that maximum bending moment is at the wall, and for the beams that we're going to deal with, that's where the maximum flexural stress would be. The other scenario, and it's kind of two scenarios. I get, well, it's one scenario. We'll just call it one. The other scenario is for the simply supported beams. And in its case, as long there is a caveat to this one. As long as your load and support reactions are symmetric, for instance, you know, you have a point load right in the middle, then the maximum bending moment is at the middle. So it doesn't have to be a point load in the center, just as long as everything's symmetric. As long as you have a axis of symmetry, you know, something like that. As long as you have an axis of symmetry, then your maximum bending moment is at the middle of the span. So the span is the distance between the pin and the roller in this case. So those two scenarios, and I was counting the other one as multiple because the loads could be anywhere. It could be a point load in the center, or it could be as long as there's symmetry about that green axis that I drew. Then your maximum bending moment is, or maximum internal bending moment is at the center of the span. All right. So that's just an aside, not really related to this problem, other than they just told us that the maximum bending moment is some number. Meaning about the horizontal axis, meaning that, you know, there's a neutral axis somewhere in this thing, and it's horizontal. So that's basically telling us the way the loads are. So the loads are going to be perpendicular to that neutral axis. Again, that's not super important to know for this problem, other than they want us to find tensile and compressive flexural stresses, and if this beam was loaded the other way, so if the beam was loaded this way, you know, where the neutral axis is vertical and the loads are perpendicular to that, if that was the case, then it would mean the loads are coming in from the side, and that is different. So they just went ahead and told us that the loads are perpendicular to a horizontal neutral axis. All right. So what we need to be able to do is use our set of equations down here to find the moment of inertia. They gave us M. They sort of gave us Y. They gave us enough information to find Y. There are two different Ys. They asked for tension, and they asked for compression. And so we need to know, is tension on the top or bottom of the beam? And what they told us is there's a positive bending moment. So the positive moments, remember, positive moments put tension on the bottom. And so that would mean that for the tension, sigma max T, we will be measuring from the neutral axis down to the bottom of the beam. They did, in our little diagram here, they did give us this value, which is the location of the centroid, which is also the location where the neutral axis is. So let's find that first. Did I loot? Nope, there it is. I need to find my calculator. So 4r over 3 pi is going to be 4 times 1.7 inches over 3 pi equals, let's see, .72. We'll go ahead and do the 1.5 since we're dealing with web work. So that's telling us where the centroid is. It's basically this dimension on our previous diagram. That distance is 0.215 inches. Okay, so that's also the distance for Y to the bottom of the beam from the neutral axis, which would be when we go to calculate the tensile stress. Now we need, remember, we're trying to solve sigma equals negative M times Y over I. They gave us M. We have some values for Y, but we need I. So when you're doing this moment of inertia I, we need the moment of inertia about the centroid. And I think earlier, when I first introduced the centroids, I said that there is a x prime and an x equation. Those aren't always, like, it's not always that you have x prime and x prime is a centroid or not or whatever. You have to look at the diagram. In this particular diagram, the x prime axis is along the bottom. You can kind of see it. It's a little bit small, but this is the x prime axis in this diagram. So that's not the one we want. We want the moment of inertia about the centroid, which in this one is Ix, and that will give us that equation. Now, it looks like I'd much rather use the x prime because it's a simpler equation, but it's not the one that lines up with the centroid, and the one that's not lined up with the centroid, in this case the x prime, you can't use the parallel axis theorem with that one. It's the way the pi r to the fourth over 8, the way that this equation was generated was by taking this equation and applying the parallel axis theorem to it. So you'd have to undo the parallel axis theorem to get back to the Ix value. Okay. All right. So we're going to have to use the more complicated equation. Let's figure that out. So Ix equals pi r to the fourth over 8 minus 8 r to the fourth over 9 pi. We'll have to plug these numbers in. My radius was 1.7 inches. Let's see if I can manage to get this in the calculator. Oh, wait. I think 0.9167 inches to the fourth. I think. I don't know. We'll have to see. I should check that, but we'll just go ahead with assuming that's right, and we'll find out later. Now we can plug that number, m and y, into our two stress equations. So sigma max T is going to be from the neutral axis to where the tension is. The tension's on the bottom of this beam. We know the tension's on the bottom because they told us that it has a positive bending moment, and we know that positive bending moments put tension on the bottom of the beam, compression on the top. So M is the same, negative, and they just gave us a number. This negative sign I just wrote is part of the equation. 21,800 inch-pounds times y. In this case, y is from the neutral axis to the bottom, so that's a negative value, and it's that 0.7215 inches. And then we have I, which is off the screen here, I think 0.9167. And these units would come out to pounds per square inch, so we would have PSI. So 21,800 times 0.7215 divided by 0.9167, I get 17,157.96 PSI. Let's see if that's the right number without, having checked any of this. I don't know. 17, well, yeah, that's more or less what we had. I had 9.6 and they have 9.9, so I think that would be okay. And it comes out positive because I have two, I have the negative sign from measuring down from the neutral axis for y, and I have the negative sign that's part of the equation, so those become a positive. So sigma max compression, same everything except now I need to measure from the neutral axis to where the compression is. So that's going to be neutral axis, maximum compressions on the very top of the beam, which is going to be my radius minus this 0.725 number. Let's see. 7215. 0.9785 inches. Okay, so everything else is the same. Negative 21,800 inch-pounds times a positive 0.9785. So this number, that's inches, this number comes out negative, which compression stresses are going to be negative. Same moment of inertia, same units of PSI. And I get a larger 23,269.67 PSI. Let's see if that, and it's negative. Yeah, that's what they have, 0.58, and I got 0.67. That's probably within tolerance for that. So the key is you might be asked a question, just calculate a moment of inertia about some random axis, and we just give you the axis. In that case, you work as if that axis is the neutral axis, and use all your, if you need to use parallel axis theorem, then you use it relative to that axis. That might be, in this case, you know, with this semicircle, if we had said calculate the moment of inertia about the diameter, the flat part, this line, that line, then we could have used that equation, because that equation is on top of that line. It's relative to that line. But if you're doing stress, if you're doing flexural stress, then you have to use the moment of inertia about the neutral axis. So for 15.1, it asks us for about the x-axis. Okay, we can look at that. Where did the 9875 come from? Yes, it was answered in the comment. It's the radius. My radius happened to be 1.7 inches for this problem, minus the that number. So yours would be different because you would have a different radius, but for me, the radius R is 1.7 inches. Let's see, so 15.1. Let's look at that. The design of beams topic is actually pretty lightweight, so it's fine to do some of this stuff first. Let's see, this is 14. Let's go to 15. Okay, so this one's got a fabricated T shape. So we're going to cheat a little bit because we're going to not do the centroid. I'm just going to look up the centroid here because it gives it to us. But then we can do some of these other. Second moment of area is moment of inertia. And then it wants to know about the X that's given. It wants to know the Y that's given. And the neutral axis. So we can do some of those. Let's see if I can get all of this copied. All right, so first thing I'm going to do is the very first thing we'd have to do, actually not to do part 2 and 3 here, or B and C, whatever. We wouldn't need this, but actually we don't need it because I wasn't going to do the centroid one. So let's skip to finding the second moment of area of the shape about the x-axis. So the x-axis is the one given. And it's kind of, you know, cluttery in here because there's all kinds of stuff going on, but there's the x-axis down there. And so it's basically at the very bottom of our T-shape. So what I'm going to do is, you know, make this into 3 pieces. The flange So on a T-beam, this part I just labeled 2 would be called the stem. On an I-beam, it'd be called the wedge. This is somewhere, not the wedge, the web. This is something in between, right? This is sort of a T, sort of an I, so I don't know what you call it, but it looks more like a web since there is a little bitty flange on the bottom. Let's see, our dimensions, we have 7. These are all millimeters. I'm gonna leave off the millimeters just to save some space. Let's see. W, I don't even, oh, W is the width there. All right. So we're going to find the moment or second moment of area, so the moment of inertia, about the x-axis, the very bottom of this thing. Why don't I get our chart for a rectangle, just so we have it. Okay, and then let's do part 1, 2, and 3. So I1 is the I1, the moment of inertia about I1 is if we want to use the parallel axis theorem, we need to be able to calculate the moment of inertia about the centroid of part 1 and then move that down to our reference axis, which is way at the bottom. So the centroid for part 1 is here, maybe there. So definitely going to have to move part 1 down to the x-axis. So BH cubed over 12 is the moment of inertia about the centroid. So the B is always relative to the reference axis. So B means base, but it's relative to the reference axis. That is normal right now, but when we do the y-axis, it'll be different. So B for part 1 is literally called B on my diagram, 70 millimeters. I'm leaving the units off again. BH for part 1 is A, BH cubed over 12, plus the parallel axis theorem, since that value that I just calculated is at the centroid of part 1 and not at the x-axis. So plus A, area of part 1 is 70 times 7, plus y squared. This y is the distance all the way up to here. That distance. So that distance looks like C plus H plus half of A. So 9 plus 56 plus 3.5. 68.5. And it's squared. So that's this equation, if I were to write out the generic version, it's not always BH cubed over 12. That's just specific for a rectangle. But it's whatever your moment of inertia normally would be about the centroid of the part, plus the area of the part times the square of the distance between the centroid of the part and the reference axis. Let's see what our numbers are. 7 cubed times 70 divided by 12. Is that right? I guess so. Plus 70 times 7 times 68.5 squared. Get a giant number, but I do have 68.5 squared, so maybe it's supposed to be that big. I don't know. 23,01203.3. These are millimeters to the fourth, so that is going to be a large number. All right, so part 2. Also a rectangle. B, the base, the side of the rectangle that's parallel to the x-axis is 10 times the height of the rectangle, looks like 56, area of a rectangle. And then the distance that I need is that distance, which is 9 plus half of 56. $37. Oops. Okay, let's see if we can get that. 56 cubed, it's going to be giant, times 10 divided by 12, plus 10 times 56 times 37 squared. Another large number, 912,986.7. That doesn't quite seem right though. Maybe, but not 100% sure. Let me make sure I did that right. 56 cubed. Okay, let me check the first one, because I would have thought the stem would have been a little bit higher than the flange up there, but maybe not. Let me just check the first one. 7 cubed times 70 divided by 12 plus 70 times 7. I guess it's because of the 68.5. Oh yeah, because we're doing the moment of inertia not about the centroid, about the x-axis. So that is makes more sense. I was trying to think of it about the centroid of the part, but we're not. All right, now the last part, I3, this one we can take a tiny shortcut. So here we actually have the part 3, and when we look at our diagram for it, we actually have one of the equations that lines up exactly with the bottom of part 3, and the part 3 is lined up with our reference axis. So in this case, we can use bh cubed over 3 as our equation without the parallel axis theorem. We could just go in and put b being 16, h being 9, over, in this case, the x prime equation is bh cubed over 3. So we only have to do that. We could do bh cubed over 12 plus ay squared, and we get the same number. So 3888. These are all millimeters to the fourth. For instance, like if we did I equals bh cubed over 12 plus area, bh, times y squared, which would be half of h. That equation, if you simplify it, you end up with bh cubed over 3. So it works out, but it doesn't work the other way. If I took bh cubed over 3 and did plus ay squared and tried to move that up to the centroid, I wouldn't get back the same thing. I guess if I did minus ay squared, I think I'd get back to the same thing. But it's best to only ever apply the parallel axis theorem to the equation that goes through the centroid of your part. Don't apply the parallel axis theorem to the x prime equation here, bh cubed over 3. It's already had the parallel axis theorem applied to it, so don't do it again. Let's see if we... Whoops, that was my calculator. Let's see if we actually got the right number. Let's see. 2301203.3 plus 912,986.7 plus 3888. So the total I about the what this was called the x-axis is 321,8078 At least that's what I calculated. Let's see the actual number. It's always a little nerve-wracking. 3218078. 3218078. Hey, I got exactly the same number that they had. We rounded to the same spot. All right, so let's do the same thing, but let's do the third part, the second moment of area of the shape about the y-axis. Okay, so why don't we recopy our diagram since it's all cluttery? And will it let me rotate it? Yes, rotate it. Well, actually I wanted to go the other way. There we go. So I'm rotating it because it might be easier to visualize what's going on here. I'm now asked to use the y-axis as my reference axis. So this is the y-axis, and x is vertical now. But you know, if you don't want to redraw the thing, then it works fine to use it, you know, the vertical way. Just recognize that your reference is now a different reference than what you're used to. So we'll use the same three parts, 1, 2, and 3. They're still rectangles. The really cool thing here now, though, is the centroids all land on my reference axis, so I don't need the parallel axis theorem. I just need the moment of inertia of each one of these shapes about their own centroid, which is the bh cubed over 12. You know, right here, bh cubed over 12. I just have to know now that b is parallel to the y-axis. So that's why I rotated it, to make it look easier to make sure that b is the base parallel to the reference axis. So I1 will be base of, oh, I don't know the numbers. A is 7 millimeters. So, well, it's right there. A is 7 millimeters. Height of what was called B before, 70. So B h cubed over 12, and I don't need a parallel axis theorem. I just need this one equation. How do we know when to use the x prime equation? The only time, oh, well, let's see, look at, so the x prime in this one, x prime is the bottom of the diagram. So it's at the bottom of the rectangle. I use that one because this piece right here, so this piece is trying to find the moment of inertia of part 3, that guy, about the x-axis, that guy, and so it was already lined up. If you're unsure, a safer thing to do is just always use the centroid one and use the parallel axis theorem if you need to. So it would have come out exactly the same. The same exact number would be b h cubed over 12 plus area, 16 by 9, times c over 2, 4.5 squared. That exact same equation, bh cubed over 12 plus the parallel axis theorem, would also give you 3888 millimeters to the fourth. So you get the exact same number. So if you're unsure if you can use the x prime, then don't use it. Use the centroid version and apply the parallel axis theorem. The rule with the x prime, or the one that doesn't go through the centroid, is that you cannot apply the parallel axis theorem to that equation. So it has to already land on your reference axis. Let's see, 70 cubed, whoops, 70 cubed times 7 divided by 12, 2, 3 zeros, 8, 3.3 part 2. Also a rectangle, a base of H, which is 56, I think. Yes. And a height of W, which is 10. So B is the 56, H is the 10 cubed over 12. I don't need the parallel axis theorem because the centroid of this part is on my reference axis, so I don't need to move it anywhere. I get 46.7. And then the final one, base of C and D. So C is 9, D is 16. So the base parallel to the reference is 9. Height of 16. $30.72. If we add all these up, whoops, wrong number in there. $207,821.97, with most of that coming from part 1. And 207,822, 207,822, yeah, if I just rounded, millimeters to the 4th. So, you know, it's probably not practical to actually rotate the picture on an exam for sure, but that might help when you're doing one of these, and if I've asked for the moment of inertia about some other axis than the one you're used to using, that might help. Had to reconnect there, it was acting weird. Let's talk about design of beams. So this is actually a pretty straightforward topic. And it could mean something like, I'm pretty sure there's some web work problems that are more design of beams. If I could, let's see if I can find one. Well, these are more about the centroid, aren't they? Or the moment of inertia. That's a tricky one, by the way. So, maybe these are not. Let's look in homework 16. Well, this one is more like a design of beam, but you'll notice the beams here are just rectangles. They're going to be easier to deal with. There's a little trick to this one. I'll go ahead and tell you that this part right here, this word nominal, is very important. So remember, let's see, is there even a note? There's not a note on this one. Remember, with dressed air dry Douglas fir lumber with nominal widths of 2 inches, nominal means that's what we call it. That's just like in the beam charts where we have a W10 by 4 and 10 is a nominal size. So what that nominal means, that word nominal, it literally means that it's the name that we use when we talk about this thing. But a 2 by whatever, 2 by 4, 2 by 8 is not actually 2 inches wide. So you have to go, I believe in your reference material, it's probably only in the test exam reference material, and look up, well, what's the actual width of a 2 by whatever. And I think it's like 1 5/8. So that makes this problem a little bit tricky if you don't catch that it's nominal width of 2 inches. All right, but this one is about a design. So you've got these beams that are essentially just rectangles, and how tall do they have to be for this load to be supported? So that one I would call design. What we're going to call is really more like selection. But what we're going to do is we're going to take a standard table. Let's find one of our standard tables. It doesn't matter which one. Let's just pick one. S. There's first. Well, I clicked on W, so we're going to do W. So I saw S, but when it moved, I clicked on W. So we've got a set of table values here for the W sections of I-beam. So W means a wide flanged I-beam. You can kind of see the cross-section example here has wide flanges on it. So what we want to do is we want to figure out which one of these is best suited for some design that we're going to do. I think, I don't know. Let's see if I want to draw an entire shear and bending diagram or skip that part or not. For practice, oh, you know what? We haven't done a cantilever. Let's do a cantilever beam with some loads on it and draw the shear and bending diagram. You don't, again, based on this morning or this few minutes ago, when you have a cantilever, whoops, you don't actually have to draw the shear and bending diagram if all you need is the maximum bending moment, because it's going to be at the wall. But let's just draw one for the sake of it, for the practice. When we're doing design of beams, you want to know the maximum bending moment because you're designing against the worst case scenario. So we're just going to do a cantilever for practice. So there's our cantilever. Okay, let's put some loads on it. Let's put here. We'll put a concentrated moment. Remember, that could be some kind of beam connection here that's got a load applied to it that's trying to twist the beam right here, or something's trying to twist the beam at this point. Let's see, the chart that I had was for US units, so let's put this in foot-pounds or kip-pounds, kip-feet, and say that it is, let's do 15 kip-feet. So it's 15,000 foot-pounds. So a relatively large external moment there. Let's put a point load. And let's make this 5 kips. That's probably enough. That's enough. We don't need to go overboard. This distance is going to be 5 feet. And this distance is whatever, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 feet. And we know that we want this to be a wide flanged I-beam, but we don't know which one. So I'll draw a little flange there. And one there. So we know it's going to be an I-beam. We know it wants to be a W, but we have all of these. It could be any one of those. And we don't want to use the worst, like the biggest one. Because that could be way overkill for what we need it to be, and it'd be way more expensive. It'd be more material, so it would cost more. It costs more to transport it. It costs more to lift it into place. And so we want the lightest weight one of these beams that will work, but we don't know if the very lightest one, like this W4 by 13, remember the 13 here is the pounds per foot. So we've got everything from 13 pounds per foot up to 230 pounds per foot. And we want to know which one of these should we get. So here's how we're going to do that. First, we're going to draw our shear and bending diagram. So for a cantilever, we haven't done any of these or haven't done many of them. The wall support is a fixed support. Remember, this is called fixed. And all three reactions occur at that one spot. So on a simply supported, 2 reactions are at the pin, 1's at the roller, but here all 3 are at a fixed support. So I'm gonna copy this, I think, and we will paste it just right here. I'm gonna do that so that I can erase all of this fixed support stuff. All right, looks like I erased a little bit of the beam. And here, that was where we had our leader line. So we'll have AY, we'll have AX, but AX is going to be 0, and we'll have moment at A. All right, so AX is 0. There are no other forces in the X direction. The concentrated moments don't create forces in the X or Y direction. So it's 0. And then we need to do something like maybe the forces in the Y direction. We could do that. I've got AY going up, and then the moments don't create forces in X and Y. So I've got minus 5 kip equals 0. AY is 5 kips. So that's easy enough. Then I can do moments about some point. I would do moments about the fixed support. So that's point A apparently. I will say clockwise is positive. I drew MA clockwise, so I'll just have MA. I drew the 15 counterclockwise, so that's minus 15 kip feet. I don't need to multiply the 15 kip feet times 5 feet. It already has feet in it, kip feet. So if I multiply by 5 feet, I'd have kip foot squared, which is not a unit I want to work with. So you don't have to multiply the concentrated moments by a distance when you're putting them in a moment equation. And then I've got plus 5 kip. That one does have a moment arm of 14 feet. The only unknown is MA. And it will equal 15 minus 5 times 14. Negative 55. Yeah. So the negative means that I drew the MA going the wrong way. All right. Let's draw our reference lines here. Again, we don't have to actually draw the shear and bending diagram. Once we found that MA is 55 kip feet, that's our maximum moment, so or negative 55. So negative internal bending moments put tension on the top of the beam. So, and that looks right. You know, we do have this thing trying to bend it upwards, but this 5 kips out here over here is trying to bend everything downwards also. So, looks like the overall effect is that tension is going to be on top of the beam. All right. Let's draw a shear diagram. It looks like we're going to go up to 5 and then down to 5. So not a whole lot going on there. We'll just call this mark 5 kips. And we go up to 5. And then the concentrated moments don't do anything. So we go straight across, we get to the -5, and we go straight down. So very uneventful shear diagram, but that's what it is. Let's calculate our areas here. So that one's 5 times 5, that's 25 kip feet. And that one's 9 times 5, 45 kip feet. All right. Oh, wait, 9 times 5. Okay. Now, let's draw our bending moment diagram. This one, I'm going to start up kind of high, because the very first thing that happens is I encounter a negative 55 kip foot moment. So I go straight down negative 55 to start with. So let's count by 10, 20, 30. Oh, let's count by, I don't know, some weird number. If I did 10, 20, 30, 40, 55 would be way down here. I guess we can do that. So the very first thing is I go straight down to negative 55. And then I have the 25 kip feet of positive shear. So I go from negative 55, I add 25, that gets me up to positive 25, which is right here. Oh, well, no, I'm still at negative 25. Negative 55 plus 25. That's not right. Should be 30, which is right here. Negative 30. It is a straight line because the shear is constant. And then I get to a positive. Oh, wait, did I add something wrong? Oh, no, that's a minus. Okay. I thought I was about to say this is a positive. This is counterclockwise 15 kip feet. So I subtract. Counterclockwise is a minus in my moment diagram. So I'm at negative 30, subtract off 15, I go down to negative 45 instantly. And then, fortunately, the last bit of shear is positive 45, so I get to 0. Like that. So this one's an oddball looking bending moment diagram, but the main point of it is that right at the wall is M max equals negative 55 kip feet. And you know that that was, one of my shortcuts up here, is that for a cantilever beam, the maximum bending moment is at the wall. So you don't actually have to go and draw the whole shear and bending diagram. I'm relatively certain, maybe, I don't know, 80% certain, that one of these, either a simply supported beam with symmetric loading or a cantilever beam, will be on the exam too, where you have to find something maximum stress or something like that, and you'll be able to do that faster if you remember that, oh, I don't need to draw the shear and bending diagram, maximum moments at the wall. Or if it's a simply supported beam and it's symmetric about the center, then, oh, I don't need to draw the shear and bending diagram, maximum moments at the middle of the span. So there's probably, I'm pretty sure, 80% chance that one of those will show up. You can solve it without knowing the little shortcut. It just takes longer because you have to do all of this stuff, that we didn't actually need to do. All right. So how do we design the beam? That's what we want to do. So let's say that what we want to find is W beam for this given loading and maybe you want to factor safety against something, maybe you don't. I'm not going to worry with the factor of safety. We're just going to calculate let's do the factor of safety equal to 2. Okay, so one thing is these beams here are American Institute of Steel. So these are steel beams. So we do have to know that these are steel beams, because that means that we need to use material properties for steel. So we're going to assume that this beam fails by flexural stress. So that we're not worried about it deflected too far. We haven't even talked about that yet. Let's say that the factor of 2 is against yielding. So normally you don't want the beams to yield. Yielding means that they've permanently changed shape. You've put so much stress on them that they are no longer going to return to their original shape. And so normally you don't want that. So we want to guard against yielding. So that means we will look up the yield strength. Our book happens to call that the elastic strength. We're going to use a generic structural steel. That's one of the materials that our book gives us properties for. So why don't we look that up first? So we'll go to our, actually we need that, but we'll come back to it, I guess. Let's look material properties here. And we are going to grab, let's kind of zoom a little bit. We don't need all those. Let's do that. So there's the structural steel, and the elastic strength is, that's what I use the word yield. And tension and compression are both the same number. Sometimes tension is different from compression, but not for most steels. It's usually a different specialized type of material. So in this case, 30 is for tension and B is for compression. That means they're the same as far as we're concerned. Oh, that's wrought iron though. Not that one. 36. So our elastic yielding strength is 36, and the units are KSI. So sigma is sigma y, 36 KSI, but we want a factor of safety of 2, so we're only going to allow 36 KSI. Well, let's write it out in equation. Sigma y divided by our factor of safety. So 18 KSI. All right, so we know how much stress we're going to allow in our beam. Now we've got to relate the stress in our beam somehow to the bending moment that's on our beam. So we have the equation that sigma equals negative m times y over I. We have that. And here, y and I are both related to the shape of the beam, like the cross section of the beam. Y is the distance from the neutral axis to the top or bottom, and I is the moment of inertia that's dependent on the cross-sectional shape. We're going to combine those into something called the section modulus. And we're going to say that S, the section modulus, is equal to I over Y. So we did I over Y so that we can plug it back into our equation and say that sigma equals negative m over S. Now, Y, the value for Y, it could be plus or it could be minus. I think they always give you the value in positive terms, but stress could be on the bottom of the beam also. So I'm going to drop this negative sign and just do sigma equals m over S, and let the I I'm not worried about is it tension or compression unless I had a material that had different properties in tension or compression. But I-beams and all the steel beams that you would normally use have the same properties in tension and compression. So in the equation S, when you combine I over Y, it is always using the larger distance. So sometimes that's a compressive, sometimes that's a tensile. The whole point is I'm not going to put the negative sign on this equation. What I'm going to do is I'm going to say that, okay, I'm going to allow 18,000 psi, so that was coming from over here, equals M, which is coming from up here. I missed. Let's see, let's do it this way. And that's 55,000 pound and then feet. I do want, look at my chart. Let's go back to our W chart. W. So W has S in it right there. But those units are inches. So I want this, instead of foot pounds, I want it in inches. So 12 inches per foot. Okay, so I'm going to multiply by 12 there. And then the only unknown is S. So I can solve for S. S will equal 55,000 times 12 divided by 18,000, 36.7. And those units end up being inches to the third power. I've got PSI over here is pounds per square inch. The pounds cancel out. I've got 1 inch over on the right hand side, 2 on the left hand, so inches cubed. So what I do with this number? This section modulus, S, is the smallest section modulus that fits our criteria. And our criteria was we wanted this beam loading, so we wanted that point load at the end, that concentrated moment, and we wanted a factor of safety 2 against yielding. Okay? So this number, 36.7, that's the smallest section modulus that will meet all of that. Anything larger works. Anything smaller fails. So then I go to my beam chart here. There are 2 columns for S, the XX and the YY version. Unless you know for some reason that your beam is loaded on the side, you know, with forces coming in perpendicular to the YY axis that it's shown, which is not common, then you're going to use the XX. And I just go through here and I look for, well, what's the smallest one that will work? So I'm going to zoom way out so I can get all of this in at once. There we go, I think. And then we will look at it over here. We'll make it bigger again. All right, so I'm looking in the column for S, which is this one right here. I've got a, let's see, let's do this. That column. And I want to find the smallest section modulus that will work. So it's either equal to or greater than 36.7. In general, these charts are arranged with the little beams on the bottom and the big beams on top. Normally, I want the smallest beam because it's less material, lighter weight, easier to transport, easier to put it, you know, that's the one that is most cost efficient. So I start at the bottom and I start marking out, nope, Close, 35.5, but nope, nope, nope. There's the first one. So 49.1. This is the first beam right here. Oops. Oh, it won't let me have a... Well, I just have to draw it by hand. Oh, well, there we go. So the W10 by 45. So that's the first beam that seems like it'll work, but what I want to make sure is that there's not a beam further up the chart that happens to weigh less. So 60 weighs more. There's a 30. So there's a 30. There's another 30. There's a 43. There's a 26. So do any of those work? I need 36.7. So this one, that works. That 30 is 42. That one's fine. That one's fine. All of those would work. So technically, assuming I didn't have any other constraints, the best beam for this choice would be this guy. The W16 by 26. Because the 26 is lighter weight than the 45. So it's a taller beam. You know, I went from 10-inch beam to 16-inch beam, but it's significantly lighter weight. And it does the job that we need. It's got a 38.4 section modulus, where I only needed 36.7. So technically, my choice would be the W16 by 26. That's the one I would choose as the best beam for this job, assuming that 16-inch beam would fit in that spot. You know, it could be that a 16-inch deep beam won't actually go in that spot. I need more headroom or something, and so I have to drop down to one of these that is a little bit smaller. But in that case, I'd go down to the either the 14 by 30 or the 12 by 30, because they would be the next lightest weight beams. And if I were getting rid of the 16 because of space constraints, then I'd probably get rid of the 14, and I'd choose the W12 by 30. Now, in the class, in the exams and web work, it only wants the lightest weight beam. So it doesn't care about the space it takes up. It's just the whole criteria is the lightest weight. So in that case, we would go 16 by 26. All right, and that is beam design. So I think we're at a good spot for calling a day. Wednesday, we're going to switch gears into a new topic, beam deflection. Let me check here. I don't remember if beam deflection is on exam 2. Oh, it doesn't tell me. That's not it. Exam 2 outline. No, it doesn't look like well, but that's a while back. So I'll have to make a decision if beam deflection is going to be on exam 2 or not. It could be that this is the last topic, but I think we have plenty of time between now when the exam is. The exam is the 25th, so that's probably long enough to do at least a simple beam deflection on exam 2. I think that's fine. So I think we'll do beam deflection 1. That'll be on exam 2, and that'll be the last topic. Deflection 2 might show up on exam 3. All right. I don't see any new questions in the chat. I think we're good. I did open up homework 16 over here with the beam design-ish type of problem statements. There will be one on the exam that is a beam design, but you won't have to draw the shear and bending diagram for it. It'll just be given, here's the shear and bending diagram, what's the best beam? So you won't have to go and draw this part out, because it's a lengthy process to draw. Even a simple one takes a significant amount of time for an exam. All right, I will see y'all on Wednesday. Oh, what is the naming convention? What is the naming convention? Oh, okay. The naming convention. So for all the beams, the W or the letter is describing the shape of the beam. So W is wide flanged I-beam. S is standard flange I-beam. WT is wide flange T. C is a channel, and L is a right angle beam. I think those are the ones we use. The the first number, 16 in this case, is the depth, the nominal. So what we call it, the nominal depth of the beam. If you look at our chart here, the beam is actually 15.69 inches tall. So depth means like from the bottom flange to the top flange. So the depth of the beam, but I would call it the height, but that's not the right word. And then the last number is how many, in this case, pounds per foot does it weigh. So this beam weighs 26 pounds per foot. The W10 by 45 is a wide flanged I-beam. 10-inch depth, weighs 45 pounds per foot. There will be 2 times for the exam, just like last time, and the virtual computer it told me to just go to virtual.latech.edu. I tried that and I couldn't make anything happen. So I think, so there's not an actual, you just log in with your regular ID. You just have to get onto that site, and I think you might have to do a VPN. So I haven't gotten that part working yet. So I'll ask again, but that's the website for it. You just log in normally. But you might, if you're off campus, you might have to have a VPN so it looks like you're on campus. And they're on the help desk site, there are instructions for setting that up too. All right. Now I think we're good. All right, I'll see y'all Wednesday.